Chapter 12, Section 2, we're learning about chords and arcs. We've learned about both of them separately before, and we're going to talk about a lot of relationships between the two, along with some angles in circles. So our objectives for today are right here: to use congruent chords, arcs, and central angles, and to use perpendicular bisectors and chords. So just so you know, we've got a lot of theorems. This is a very theorem-heavy section. We're going to give one or two examples to help with the theorems as we go, but we're probably going to get through 6 or 7 theorems in this section, just so you know. So get those theorem sheets out. All right, but before we go, a chord. So a chord, and we've talked about these before. A chord is a segment whose endpoints are on a circle. So technically a diameter is a chord, but we do not call it a chord, we call it a diameter. But any other lines that go from one end of a circle to another makes a chord. In the circle to the right, PQ is a chord, and its related arc, PQ. I don't know why I wrote an R. I meant P. So the arc is PQ. There's always an arc that goes along with a chord. We're going to find there's also a central angle that goes along with that as well. So, essential understanding for this lesson: you can use information about congruent parts of circles or congruent circles to find information about other parts of the circle or circles. So let's start off with a few theorems. First of all, theorem 12.4 says, and I'm going to give you the converse. Most of these, the converse are going along with them. So the theorem is, within a circle or congruent circles, we're just going to deal with a circle for right now, congruent central angles have congruent arcs. So for instance, on the circle to the right, the congruent central angles would be AOB and COD. So we have that here. So if angle AOB is congruent to angle COD, then their arcs are congruent, the ones that go with it. So then arc AB is congruent to arc CD. And vice versa, the converse, the backwards of that, within a circle or congruent circles, congruent arcs have congruent central angles. So if we know the two arcs are congruent, then the central angles that are attached to those would be congruent as well. So angle AOB would be congruent to angle COD. That is theorem 12.4 and the converse. So theorem 12.5, moving on a little bit here. Theorem 12.5 says, within a circle or congruent circles, congruent central angles also have congruent chords. So we're still dealing with congruent central angles, but their chords that are together would be congruent as well. So in this case, if angle AOB is congruent to angle COD, then chord AB is congruent to chord CD. And its converse, congruent chords have congruent central angles. So if we know that segment AB, the chord AB is congruent to CD, then angle AOB is congruent to angle COD. And one more theorem for this page. We're going to get into something with the, we're going to combine the arcs and the chords now. So within a congruent circle or congruent circle, or within a circle or congruent circles, congruent chords have congruent arcs, and the converse congruent arcs have the congruent chords that go with it. So if we know that AB is congruent to CD, then the arcs that go with it. Arc AB is congruent to arc CD, and vice versa. If the arcs are congruent, then the chords are congruent. AB is congruent to chord CD. All right, and a lot of these things, a lot of these theorems, at least the first few, personally I think they just make sense. They're kind of common sense theorems, but they are stated in a theorem. They're actually proven to be true for all circles or congruent circles. So a couple examples here. First of all, the first example says, if the two circles are congruent in the picture there, what can you conclude? So we have congruent circles, and we're given that the central angles are congruent. So then, if congruent, if central angles are congruent, then we can deal with these first couple. Then the arcs are congruent, and the chords are congruent. So the arcs would be arc F, well actually arc AC, you can look at it that way, would be congruent to arc FH. And same thing with the chords. Chord AC is congruent to chord FH. Okay, that's just the first two theorems we had there. Now, question 2 is a thought question. Why is it important that the circles are congruent to make your conclusions in example 1? So think about it. If you think about it, if they're not congruent, if you had a larger circle, I mean, we could still have a congruent angle, but the arc is going to be a lot bigger because it's just a naturally bigger circle. So it has to be congruent. I mean, you just look at the theorems. The theorems say it has to be congruent circles, but just as an example, bigger circle would be bigger arcs. It might necessarily, you can still have the same angle, but the arc is just going to be naturally bigger. All right? So they have to be the same circle or congruent circles. All right, another theorem. Theorem 12.7. Theorem 12.7 and its converse. This one says within a circle or congruent circles, chords equidistant from the center, or centers, are congruent. So if we look at the picture to the right, let's break that down. If we have two chords and the same distance from the center, then those chords have to be the same length. And its converse, if the chords are the same length, then they're the same distance from the center. This one, maybe didn't think about this before, but this is one that we're going to use. So we know, if we know that OE equals OF, so those two lengths are congruent or equal, then we can say that the chord AB is congruent to the chord CD. Same thing goes backwards. If we have that AB is congruent to CD, then they're the same distance from the center. So EO, the distance is E, well, I guess it's OE we're using, has to be equal to OF. Or you could say that their segments are congruent. Two examples. So let's look at example 3, and then I'll have you, well, we'll look at an example 4. I'll have you do example 4. Example 3, we have two chords, and they're both 18. That and that are 18, so they are congruent. That means that they're the same distance from the center. So if one of them is 8, then the other one also has to be 8. 8 units from the center. All right, number 4, I'd like you to try on your own. It gives you how far they are from the center, and they are the same distance. So what does that mean x is? All right, if you look at it, x is just a half of this chord. So if this chord is 25, half of it obviously would be 1/2 of 25, which is 12.5. All right, going on. Guess what? I think I've got 3 more theorems for you. And these are the ones that get a little more tricky. So really think about these. Theorem 12.8 says, in a circle, if a diameter is perpendicular to a chord, so again, we've got a diameter, and it's perpendicular to this chord CD here. It's labeled by this. Then, what do we know? It bisects the chord and its arc. That means that these are congruent if it bisects that. That means that CE, segment CE, is congruent to segment ED. And it also bisects the arc. We don't usually bisect arcs, but that just means that the arc lengths would be the same. So that means that arc CA would be congruent to arc AD. Apologize if that's a little messy. But the arcs are also congruent. All right, theorem 12.9. Yeah, again, we're dealing with these perpendicular things. So in a circle, if a diameter bisects a chord, assuming that in this case it can't, not looking at different a diameter, just if it bisects a chord that's not a diameter, then it is perpendicular to chord. Because this is almost the exact converse. All right, so if we know that if it bisects just the chord that we have here, then we know that they're perpendicular to each other. So segment AB, which was the diameter, is perpendicular to the chord CD. Okay, makes a right angle. And lastly, the last one I think we're going to do today. This one, Theorem 1210. In a circle, the perpendicular bisector of a chord has to contain the circle, or the center of the circle, meaning it must be a diameter. In other words, it must be a diameter. Okay? So there's not much more than you can say about that other than AB goes through the center. All right. Whew. So let's look at this first example here. Just taking a step back, looking at what we just learned from all those theorems. And it says in the diagram to the right, ST, segment ST is a diameter, and segment ST and QR are perpendicular. So we said if they're perpendicular, the only things we can make conclusions on are that it bisects the chord. So QU would be congruent to UR, those segments. It also bisects the arc. This arc is congruent to this arc, meaning QT, the arc QT, is congruent to the arc TR. All right? Now, this one's going to be a little bit of an application here. Let's look at this one. Find the value of x. So I'm going to actually have you look at it for a while, pause it, try to find the value of x. See if there's anything you can do to figure out the value of x. All right, my guess is that you had a hard time with that because I had a hard time with that the first time. And this isn't the first time I've done this before. So if you look at it, we don't have any theorems up here that deal with the length from a chord to the center or a chord to the diameter. Other than if we know there's another chord and they're equidistant, then the equidistant from the center, then the chords are congruent. But we don't have another chord. So we're trying to find x. The only thing that I could think of doing for this one, this might seem crazy to you, but if we're looking at this and we have a right angle, we have two sides of a right triangle if we use that. Then we can make a third side. And the nice thing about that third side is, well, first of all, we know that this is 5 for the one side because it's half of that 10. On the third side, we also know. How do we know the third side? The hypotenuse. Well, it's a radius. And according to the diameter of being 24, if the radius would have to be 12. So we're just missing one of the two legs. So the Pythagorean theorem, 5 squared plus x squared equals 12 squared. And we can simplify and solve, hopefully, for x. So subtracting 25 from both sides. X squared equals 119. All right, that's not pretty. So we're going to say that x is just equal to the square root of 119. Which my guess is it'll be just under 11. Okay? So that doesn't quite look accurate if you're looking at it. Hopefully it is, though. If you have questions on that, please ask them next time. If you find a mistake on that, make sure you let me know. I'm not going to look back at my mistakes right now for the sake of time. But I would like you to go on and answer these 3 closing questions. If two central angles are congruent, what can you say about the arcs and the chords they create? What is true about two congruent chords in a circle? And then finally, if a diameter is perpendicular to chord, what is true about the chord and its related arc? All dealing with those theorems we dealt with. And then go back and look at the objectives and kind of self-assess, see what you learned, see what you can remember, see what you can do with these chords and arcs. That's section 12-2. We'll see you next time.